does that graph look like? Or should I say, what does a graph of this equation look like?
Circle.
What's circle?
Unit circle.
Sphere.
Specifically, well, sphere is free space.
Oh.
Specifically the unit circle, because the circle is radius 1 and it's center at the origin. And I think it looks something like this. What do you think you can say about the following? What do you say about the coordinates? Nice, nice, nice. So we've got the cosine of t, comma, the sine of t. You guys there? Is this true?
Yes,
Why?
because it's an identity.
Oh, where's the identity come from? Well, it's the Pythagorean identity, is what I call it.
It's the hypotenuse of your triangle when you do the extent.
I'm too tired. I don't want to think that long. Be more lazy. Trick teachers, don't yourself. Well, you guys, look. If those really are the cores at that point, they're points on the graph of that equation. You plug this red thing in for x, you plug the purple thing in for y. You guys see it? Trivial? That was so much fun. Let's do it again. That was called unit circle. And so you guys called these functions, you called them. Oh, you're killing me.
Hyperbolics. Conics.
Circular.
I heard that.
Alright.
You call them circular functions, they came from the coordinates of points on unit circle. That was so much fun. Let's do it again. It's the same darn thing. It's just that we're going to look at points in the graph of not that equation black on the top of the left board, but maybe this one instead. It's so special. I'll give it a name. I'll call it my unit hyperbola. And I think, graphically speaking, looks just like this. Where this point right here is, well, not that. 1 comma 0 and 0, negative 1 comma 0. It's just that in the rightward branch, I will think of points on this unit hyperbola as being associated with some parameter. I'll call it t again. I'm just going to refer to its coordinates in the following fashion, just like I did before the cosine of t, comma, the sine of t. Oh, you're right, it doesn't work, does it? I've already used those red and purple beats for the coordinates of those points over there. I'll change my language a little bit. I'll think of the first one as a hyperbolic sine of t, cosine of t, and a hyperbolic sine of t. It's one way to define those functions. It's not the only way, but it's one way of doing it. In another way, to be more algebraic, and to be more algebraic, you and I talk about the cosine, I meant hyperbolic cosine of t and hyperbolic sine of t. I could define it in the following fashion. Now, you guys don't take this the wrong way. Look. When it comes to the graph of the cosine function, is that the graph of a unit circle? No, of course not. It is a sinusoidal wave. The graph looks different for the equation y equals a red beast as opposed to the equation unit circle. It's just that I use the unit circle to represent the cosine of t as the x-coordinate point on the unit circle. Likewise, don't think of this as a picture of my hyperbolic cosine or sine functions. This is just simply a pictorial way of representing hyperbolic cosines and sines. To graph this beast right here, what am I going to do to sketch the graph out of thin air? Even if you've never seen this before, how should I graph this beast?
Plug in values for t.
I always get tired when I do that. I make silly mistakes. Very nice. For hyperbolic cosine, let's do this. T-axis. Y-axis. You guys, I want a yes or no answer. Is that easy to graph?
Yes.
Yes.
Piece of cake. Where's the x-intercept?
There's no
There isn't one. Where's the y-intercept?
1.
0, 1. Where is the vertical asymptote?
There's no.
There isn't one. Where's the horizontal asymptote? Y equals 0 on the horizontal t-axis. Help me with this. What does this one look like?
Opposite.
What do you mean we
We're
were
thinking about the y-axis.
A reflection about the y-axis. I think it looks something like this. What does the graph of this going to look like?
E to the t raised to the negative e to the t.
Is it raised, or I thought I was just adding these together?
Well, that's 1 over e to the t.
Mila, what are you doing? Why are you doing that? I was hoping you're pinching your fingers, suggesting that if x is, if t is really, really big, what do the y values in the graph of the dotted curve do to the y values on this red equation? Good, in other words, hardly anything. So I think, in the right-hand plane, the solid black curve is acting as an asymptote for the graph of the red equation. Because as t gets significantly large, I think the y values in this dotted curve are pretty darn insignificant. And maybe when t is finite, it has more of an effect, but certainly in the right-hand plane, it doesn't. Same thing with the curve in the other plane, in the other half plane, I should say, excuse me. I think this graph, that's the graph of the red equation. Oh shoot, did I just make a mistake? That's not what I want. I really wanted this. So tell me in words what it looks like, in words. Maybe not a shift, but a compression towards the horizontal t-axis by a factor 2, and therefore it's going to look something like this. I think that's what my hyperbolic cosine function is going to look like. Notice how the y-intercept is a 0, a positive 1. Notice that there are no y values in the graph below the y value positive 1. Is that curve significant at all? Does anybody know?
It's a catenary parabola.
We call it a catenary curve, but where does it pop up in nature? What's that?
Optics.
I don't know the answer to that question. I don't know if it does. I typically associate the conic sections with optics. Potential what?
Bridge.
Yeah, I like that. If you take two people, you're not having seizures, be nice. And you have a rope or a chain in between them, and there's a natural sag. I think that natural sagging is due to a function that looks just like this. Okay, I'm being a little silly. Maybe it looks more like this. In other words, maybe the coefficients are all changed. But that's the underlying basic curve. Again, we call it a catenary curve. Notice something interesting about it. It's transcendental. I'm not expressing this in terms of addition, multiplication, subtraction, division. It's definitely not algebraic. What's really interesting about this is that if I evenly disperse weights along this curve, it changes its curvature. Like, for example, putting a roadbed underneath a cable, for like a cable bridge. It changes curve's shape, so they can be mathematically modeled like this. Oh, come on, nobody jumped. I mean, you guys don't have that many relationships between transcendental functions and algebraic ones. That is such a relationship. Oh, wait, hold it. You don't have any good relationships because we're not in chapter 8 yet. But you have a lot of really good relationships that you've done this semester. So basics of hyperbolics. By the way, check this out. Because this is the equation of my hyperbolic function, here is my most basic identity for hyperbolic functions. Namely, the hyperbolic cosine squared of t minus the square of the hyperbolic sine of t is equal to 1. Where the heck does it come from? And you deep REM sleep. It comes from picking up these two colored beasts, swapping it for x and y up there. And from here, I can generate all my addition, subtraction, double half identities for these hyperbolic functions as well. They don't look just like the ones with the circular functions because the sign change here, but they're very similar.
So, Yeah.
Oh, I'm getting there. It's gonna take me a while. And it's certainly, Alex, gonna take you more than today.
Okay.
But I'm gonna get us started today, since somebody asked. Well, you guys take a peek at my purple graph. Do you think that function has an inverse?
Yes.
Say it again.
No.
No, why not? Say it again.
It fills the vertical line.
Oh, a little louder.
It'll have two horizontal planes.
Thank you. And so this is gonna fail the horizontal line test.
Oh.
So you're right. I think this function does not have an inverse. I got an idea. Let's cheat. Let's make a restriction. Let's allow x to only, or t to only be positive. Then I do think that's a one-to-one piece of the original curve that really span all the y values from 1 on up. I think that will have an inverse. Let's generate it. Generate its inverse. How did we do that back to? We rewrote this by interchanging variables. Can you guys read the sloppy writing? Mouse of y. How do I solve for y? Yeah, get rid of fractions.
That's going to be 1 over e to the y.
Oh, so you're saying I didn't get rid of fractions yet? I agree. That last term could be interpreted as a 1 over e to the y. Oops. So I'll multiply both sides by e to the y.
Now it's just
Now it's just, I didn't catch that, I really didn't.
it's
It's quadratic.
yeah,
Very
that's
nice.
the one.
And since it's quadratic, let's put it in standard form. And let's see when I solve for e to the y. Is that going to be my negative b? Plus or minus the square root of b squared? Minus 4ac. All over 2a. Or shall I say e to the y is merely 2 plus, I misspoke, didn't I? I meant to say x plus or minus the square root of x squared minus 1. But you guys, over here in this picture, notice that x was strictly positive and y was strictly bigger than 1. So when I interchange variables, I think y is going to be strictly positive, x strictly bigger than 1. That immediately tells me I've got a restriction. I've only got the positive component square root. And in solving for y, I see that y is a natural log of all this stuff. Ah, shoot, you guys, can I just cut to the chase? Let me declare what we just found. We found the inverse hyperbolic cosine of x. Makes a lot of sense, doesn't it? The original hyperbolic cosine could be interpreted in terms of exponentials. Therefore, since natural logarithmic functions are inverse of natural exponential functions, then I think I should be representing this inverse hyperbolic cosine in terms of the natural log function.
Why is
And
it
there it
natural?
is. What's that?
Why is it natural?
Because of the way I define hyperbolic cosine in terms of natural.
No, I mean in general, why is it natural log versus, what's so natural about natural?
It's huge, it's huge. Can you tell me what the natural log of x is? As a function.
Log base e to the
It is, but how'd you define it back in algebra?
the relationship to the exponent and
Beautifully put. Alex is saying we defined it as the inverse of the natural exponential function. That is not the way I was raised. In mathematics, I was raised to defining the log of x in this fashion. T-axis, y-axis. In the right-hand plane, I got a half a hyperbola. If you allow x to be strictly positive, then taking a peek at this position on the horizontal t-axis, in this position, there is a certain amount of area under that curve. The area can be interpreted in terms of this definite interval. We give it a name. We literally define out of thin air this to be the natural log of x. That is how I was raised in mathematics in terms of defining that natural log function is an area grabbing function. And I promise you, if you erase all knowledge of the natural logarithmic function, if you redefine your log function this way, you can generate all the properties of logarithm out of thin air using this definition. Really slick stuff. And as a matter of fact, it's kind of surprising to me that the real serious upside to this book is that a chapter or two before, I forget, somewhere last week, one of those chapters, he had a couple sections at the end of that chapter dealing with just this one issue. I'm kind of surprised because I haven't seen it for years. All the Aussie's texts skip this whole approach. And we just rely on defining the natural log function as nothing more than the inverse of the natural exponential function. But David, I was attacking your question. You were saying, what's so natural about it? I think that's beautiful relationship. That's really slick stuff.
So how does the E play into that particular definition of it all? Because if I knew nothing about natural logs and that they undo the actual
Natural exponential function.
The natural exponential function.
Then you would just treat this a whole new process out of thin air, nothing to do with exponential functions, where this is how you're going to define the natural log of x. I feel like I'm not answering your question.
Well, the E is introduced as part of the natural log.
Now I think it was introduced because of what you said a moment ago. If we define the natural log function as the inverse of the natural exponential function, I'm adhering my natural log to E. I'm saying with this definition, you're going to think of the number E if you're going to treat this as your definition. It'll naturally pop out later on. I'm just saying, initially, this could be the seed of all your theory behind natural log functions. And notice I did not mention Lewis constant. It's, what I intended, naturally embedded in there because of the curvature and so forth, but you don't see it symbolically. All right, what is worth you guys? But when it comes to hyperbolic functions, I'm not nearly done. I've got tons to say. Can I just say one more thing before we stop? Just one more. This is really cool. This is really slick. If you differentiate the first term, don't you get this? The second term, don't you get this? Oh shoot, I forgot the constant. But that's just hyperbolic sine of t. If you were to come down here, differentiate, wouldn't you get this? So the derivative of hyperbolic sine is positive hyperbolic cosine, but the derivative of hyperbolic cosine is positive hyperbolic sine. No, just so immediate, isn't it? Because of the way I define them in terms of the natural exponential function. Okay, I am so not done. I haven't talked about very special types of integrals. I certainly want to talk a heck of a lot more about the natural log expressions like this. I'll get there, I promise. In fact, maybe I should finish up tomorrow. So tomorrow, if you guys are going to get ahead of me, can you slide into section 7.6, which is what I meant to discuss today. It's just that officially now, 7.6 is not on the exam. The exam only goes up to 7.5. And if you need more practice, dive into the exercise set I had online. What's that? Yeah, the next one.
Do you have the next week's exam, next exam posted?
No, sir, I completely forgot about it. Are they?
Yeah.
I must have done it for your last exam. Thanks for checking.